Okay, so this is our final session for this class. And so what I'd like to do is cover whatever is of question for everybody. I can hit the last couple of chapters if you want, but before we get into that, just to recap what we're going to be doing, I'll send out a note this afternoon with this video that just gives the specific information about the meeting, not great detail there, but I put in the note that I sent to you about this meeting, 622 8th Street, Marietta. That's where we'll get together. It's, if you're curious, if you Google Earth it or whatever, you'll see it's a residential neighborhood. It's an orangish style Victorian house while we get together. We're going to have a relatively small group. I think we're going to have 7 people. So it's not like we're going to be overcrowded. We're going to do the labs back in the carriage house building, which is eventually going to be our training center, but you'll see it's a gutted, empty building at the moment. So there's space for us to do all of the labs. But then when it comes time to do our exam review, we'll come into the house where it's nice and warm, and we'll have coffee, and we'll sit in comfy chairs, and we'll look at my presentation, and we'll review everything, and then you'll take the test. So we'll do the test inside. We'll do the hands-on out there at the carriage house. So we got you covered. There's plenty of street parking out front. They just cleaned up all the leaves today, so there's not even leaves around. So that was nice of them to clean up the leaves before our workshop. And then I'll deal with lunches. So I'll just order pizza or sandwiches or something for everybody, so that we don't have to disperse. We'll provide coffee and tea, and all you guys need is dress comfortably, bring your attention, and we'll provide tools. We'll provide pretty much everything that you need. So for the session, the schedule we'll begin 8 o'clock on Saturday, and we'll go straight on through until we finish up all the labs. Normally we can be done by 4:30 in that neighborhood. Sometimes it takes all the way till 5, occasionally 5:30, but that's mostly my fault if we're talking too much or playing around or whatever. But we'll get it done. And we'll break for lunch probably about a half hour. That's one of the nice things about having the lunch brought in. We don't all lose an hour while everybody's running out, or an hour and a half finding a restaurant or whatever. If you've got dietary restrictions, I'd suggest either letting me know or bring in your own food. That's often easier if you've got allergies or don't like pizza or whatever. And so we'll do that on Saturday. Then Sunday, we'll start again at 8 o'clock. We'll spend about 4 hours reviewing and answering any of your questions. And then we'll eat something, and then we'll take the test. You have 2 hours to take the exam. There are 75 questions. Their questions are very similar to what are in the back of each chapter. So if you're comfortable with doing the questions at the back of each chapter, you should do fine on the exam. I would say, if anything, the questions I have in the book are a little more difficult, only because some of them are designed to be a little tricky, or because I want you to miss them. I want you to learn from having screwed it up, as opposed to, you got every one of them right and maybe you don't remember. But the test is not designed that way. The test is not designed to be confusing. The questions are not in a negative format. Like, I have a lot of questions says, which of the following is not something? And on the exam, they would not do that. They would have it in the positive, because sometimes you miss the not when you're reading it. So you have 2 hours. You won't need all 2 hours, but you have them. And then 75% is the passing score. So if you get a 75%, that's the same as getting 100%. It's a pass fail kind of situation. I will say I've only had 2 students in all the years doing this now that have gotten 100% on the test. And one was a monk, and one was a young woman who just got out of the military. So I don't know what that tells you, other than I've had a lot of people who have only missed one. So that's, so it's
Mhm.
it's normal to just miss one. Not I mean, it's unusual to get that good a score. Most people pass by a few or fail by a few. That's sort of it is almost a true bell curve. When you look at the results over time, and that bell curve peaks right there somewhere at I'd say around 77%. So it's a little bit biased towards passing, for sure. But that's just dependent on the amount of work you put into it. This is a new language. Um, I don't think this group's motivated, but when I teach at a college or a workforce development place or something like that, a lot of the people are not motivated. So if they don't put the time in, if they don't read the chapters, they're not going to pass. So that's that's the sad reality. Okay, any questions about the test, the process? Oh, I should have said after you do the exam, after everybody's done, we're going to do a small install. So if you want to get a sense of it, you're welcome to stay on. I mean, it's not required. It's just there as an add-on. So probably about 2 o'clock, 2:30, somewhere in that range. We'll go out here at 622 8th Street here in Marietta, and we'll add 4 panels, maybe 5. I have to find out about the panels to our current solar array. So we will be adding capacity to that. So I don't anticipate that build's going to take more than 2 hours, because one of the things you learn in this course is about future proofing. And when we installed it the first time, we anticipated that we would be adding more panels at some future date. So these are end phase microinverters. So we've already pre-wired everything so that all we
Mhm.
have to do is put up the railing, mount the microinverters, attach the panels, and then hook up. The wire is the wire that we're going to hook to is already up there. It's zip tied to the existing solar array. So we just have to unzip tie it and string it out and run it up and cable manage it and plug in, and we're all set. So there is no pulling of wire or anything like that. It's really just mounting the panels and getting a sense of that. So we're going to do that. Any questions about that process? Yep. Okay, so let's throw it open. You guys should be pretty close to being done with the book. Certainly by this time you show up on Saturday, you should be done. And has anything come up in your studying or in your online that you have a question about?
Yeah, I have a question with some of the math.
Uh-huh.
Maybe I'm missing a concept, but most of the time when you're dealing with percentages, you move the decimal plate two places, and then when there's one place where when it's a 16%, but then when you do the multiplication, you just move it one place. It's 1.6 instead of. So I'm a little confused.
Oh, 16%. Um,
Yeah.
yeah, I need to see the exact on that, because obviously when you decimalize 16%, it would be 0.16. So if it's 1.6, that sounds like it would be wrong. Um, because
Yeah.
to turn a percentage, you divide by 100%.
Yeah. Well,
Um,
I'll email my question after the class. Yeah.
okay. Yeah, I would say that most people have, when they're concerned about passing the test, it's usually concern about the math. That's because it's one thing to say, okay, I can remember that Becquerel was involved in defining what the photovoltaic effect is. And it's funny because, speaking of Becquerel, and this is just my own, it's a bit of an aside, but if you read through a lot of textbooks, a lot of online things about who is credited with discovering the photovoltaic effect, you'll always see it referred to as Edmund Becquerel. And you'll notice in my book I talk about Alberto. Is it yeah, I think it's Alberto. Anyway, it's the father. Um, and that's something that just annoys me because uh,
Mm.
essentially during the 1800s when this thing was done, I think it's 1830 something. Um, the reason why they give Edmund Becquerel credit is because he later went on to become the more famous scientist out of the family. He ended up winning the Nobel Prize for Physics for his work on radium with Madame Curie. Um, but at the time, he was 17 years old and he was working in the lab with his father. Well, I don't care if he was the boy genius and he did all of the work, his dad still gets the credit. This is the early 1800s, so the boss is always going to take credit for the work that the underlings did. So
Everybody else named Al.
yeah, yeah, it doesn't change.
At Al. Although I think they've gotten away from that a lot.
Well, you're not going to give credit to a 17-year-old if you're paying
That's
his
true.
wages. so
Yeah.
so anyway, so that's just my own bias, but on that. So yeah, but the math, there are probably 8 or 9 questions on the test that I would say are math based, where you do the calculations. And just as a heads up on that, voltage drop is going to be one you're going to need to understand how to calculate. And
Yeah.
voltage drop is just a variation of Ohm's law. Volts equals amps times resistance. And well, let me go ahead and share the screen here.
Are we
Uh,
going to need to bring a calculator?
I've got little cheapy calculators that I'll give you.
Mhm.
Um, but if you have a calculator that you like using, feel free. Feel
Okay.
free to bring it. A lot of people
Is
do.
it,
They've got their Texas Instrument thing that they like or whatever. But
is it
I've got
okay
some.
to is it okay to use the calculator that's just built into your phone?
No.
That's the one oh, okay.
Yeah,
'Cause
you're not
that's the one
allowed.
I use.
Yeah, because your phone has other functionalities such as access to
It's
the
true.
internet where you can look up all the answers.
Mm.
So, no, they want you to
Where'd
just
that
use a
go?
regular old calculator. So, so the equations that you're going to have memorized, one of them is watts equals amps times volts. So that's the power equation. Hopefully by now that's kind of second nature to y'all. If you're an electrician, you'll often see that referred to as pi, P equals I times E. It's the same equation. The old thing, electricians like pi. I mean, but it's power equals amps times electromotive force. They're just using power in exchange for watts. Watts is power.
Mhm.
Amps is amps. And volts is just an electromagnetic force. So it's an intensity of the current. So um, that's the power equation. Watts equals amps times volts. The second one that you're going to want is right? Volts equals amps times resistance. That's Ohm's law. And all these are doing is saying that if you know two of them, you can figure out the third one, right? There is a relationship between these numbers. And you can do the Ohm's law triangle, but it works with all of these. If I say watts over amps and volts, this is just a short way of not doing the math, not knowing algebra. So if I cover over watts, it's going to be amps times volts. If I want to know amps, it's going to be watts divided by volts. If I want to know volts, it's going to be watts divided by amps. So you can just visually see the algebraic relationship between that.
Mm.
Ohm's law is going to be volts over amps times resistance. It's the same thing. Volts equals amps times resistance, which is what I wrote out here, or resistance equals volts divided by amps, or what's the last one? Amps equals volts divided by resistance. So it's just visually what you're seeing there. That's all the Ohm's law triangle. The third equation is the voltage drop, And voltage drop equals amps times resistance times twice the distance divided by 1,000 feet. Well, all that is Ohm's law, right? Volts equals amps times resistance, but it's adjusted for distance. Why is it adjusted for distance? It's because the resistance that we're given, we get that out of the National Electrical Code, and it's giving us resistance for a particular wire per 1,000 feet. So if I say that my calculation, if I'm using number 10 stranded copper wire, and I know the resistance is 1.24 ohms, well, that's 1.24 ohms per 1,000 feet. Now I need to know what portion of 1,000 feet I've got. Well, I take twice the distance. Why do I do twice? It's because it's a circuit. The electron goes there, the electron comes back. So the electron is traveling twice the distance, twice the physical distance, divided by 1,000 feet, right? Because that's the number we were given. If you put a measurement on it and you actually measured resistance, you wouldn't worry about all that. You just do Ohm's law. But because we're getting our resistance based on units of 1,000 feet, we need to make that adjustment. So these are really the only three formulas you need to have sort of memorized in your brain.
Mhm.
And I think they're pretty straightforward. The voltage drop is the only one that's a little bit complicated. But if you think that it's just Ohm's law adjusted for distance, then that's easy. Okay, so what are some of the other questions other than voltage drop? Well, one of them you're going to need to know is, how do you size an array? So how do we size an array? Well, the trick is usually, how do you get started on these things? So sizing an array, you basically take your daily load. So when you're sizing an array or you're sizing a battery bank, we're always going to start with our daily load. And what do we do with that? Well, we take our daily load and we divide it. We want to get from kilowatt hours, because that's what we get when we get a daily load. So in this case, we're wanting to go from kilowatt hours per day to kilowatts. That's how we measure an array. So how do we get from kilowatt hours per day to kilowatts? Well, the first thing we divide by is hours per day. How many hours per day? Well, it's not going to be 24. It's going to be hours per day of insolation. Pure sunlight. Insolation. Okay? Well, we get that from PV watts, right? Once we have that, then we want to divide it by the efficiency of the system. So we're derating. Because what this would do is give you the amount, the size of the array if it were 100% efficient, but it's never going to be 100% efficient. So what's the efficiency of the system? And then that gives us our answer. That's the array size. So sizing an array is pretty straightforward. So for instance, if I wanted to know what size array I need, and I'm told the daily load is 30 kilowatt hours per day, and I'm told that at this location, there's 5 hours of insolation per day. Well, and I'm also told that this system is, let's just say, 92% efficient. I would take 30 kilowatt hours divided by 5 hours, and that's going to give me, what, 6? So this would be 6 kW if it were 100% efficient, but it's not. So now I divide that by 0.92, and now I've got to grab a calculator. So I would say
15, 16.
6,000 divided by 0.92, 6521 or 6522. So it's 6.522 kilowatts, or 6,522 watts. So if you get a smaller number, you multiplied by the D rate, you didn't divide. And logically, that just makes sense because if the system's not 100% efficient, you need a bigger system, right? You don't need a smaller system. So it doesn't make sense if you don't get all the power you're producing, so I can get by with a smaller system. Well, logically, that flies in the face of logic. So
Mhm.
this is a common mistake. People multiply times the D rate and they end up with 5.4 or something like that. Well, hopefully you'll catch that because you need a bigger system. So once again, when you're figuring out the array size, and we do this all the time, daily load divided by hours of insulation divided by the efficiency of the system. Pretty straightforward. Any questions about that? Now that I've told you it's easy, you don't want to step up and say, I don't understand what you just said. But
Mhm.
okay, so the other one that's very similar to that, but a little more complicated, has to do with lead acid batteries. So with lead acid batteries, how do we get started? How do you size a battery bank array? A battery bank. Well, once again, we're going to start with our daily load. How much are you needing to power? But remember, our daily load starts out at kilowatt hours per day. And we want to get not to kilowatts now, we want to get to amp hours. So how do we get from kilowatt hours per day to amp hours? Well, first thing you're going to do, kilowatt hours per day, to get to amp hours, we would just divide that by the voltage of the system. So we would take our kilowatt hours, divide by the volts, and that would give us amp hours per day. Does that make sense? Because watts equals amps times volts. So if we divide kilowatt hours by volts, we get amp hours. Amp hours per day. Well, then how many days? Let's multiply it times the number of days of autonomy. Now we're going to get amp hours. And if the system were 100% efficient, and if we could use 100% of the battery, that would be our answer. But we can't, and it's not. So now we have to divide it by depth of discharge. How much of the battery are we going to use? So we divide that by depth of discharge. We're still going to get amp hours, and now we divide that by the efficiency of the system. And that gives us our answers in amp hours again. So we would be done if it were 100% efficient and we could use the whole battery. With lead acid batteries, what you're going to find, if it's a standalone system, you're going to be using maybe only 50% of the battery. So your depth of discharge is going to be around 50%, maybe 60%, maybe 40%. So we have to do that. So let's use this as an example. Let's say that we're going to use that same house and we have a 30 kilowatt hours per day load. And it's a 48 volt system. So 30 kilowatt hours or 30,000 watt hours divided by 48 volts gives me, is it 625 or is it 62.5? Let me make sure. Divided by 48. It's going to be a big system, right? 625 amp hours per day. Did I do that right? And let's say that we decide we're going to go to, let's use 80% of the battery, right? So we're going to go to an 80% depth of discharge. So I would divide that by 0.8. And now it's 781. 0.25. One thing I didn't do, I skipped over the days of autonomy. If I wanted 2 days of autonomy, or let's just say we only need, I don't know, 6 hours of autonomy, because this is a big battery. Well, what would I do? I would multiply that times 6 hours is a quarter of a day, right? So I'd multiply it times 0.25, trying to bring this down in size to something manageable. So now it's a 195 and some change amp hour battery. But now I have to derate it. And if my system is only, say, 75% efficient, 195 amp hours divided by 0.75, and now we're 260. So I need a 260 amp hour system under this scenario. Well, what does that mean? Well, I got to go out now and buy a battery. Well, what if I went out and I found a 275 amp hour 6-volt battery? Well, I could get by with one string, right? 275 is a little bit more than 260, so I'm fine there. But I need 8 batteries because it's a 6-volt battery, but it's a 48-volt system. So I need to hook 48. I need to hook 8 of them together in a string to get the voltage up to my system voltage. Does that make sense? So if the question was how many batteries do you need?
Yeah.
In this case, I would need 8. If the question was how many strings do you need? I would need 1. If the question was how many amp hours does the system need? What size system? Well, it'd be a 260 amp hour 48-volt system. Okay, so that's how you size lead acid batteries. The nice thing about working with lithium ion batteries in this world that we're in today, we don't go through all these steps. You know how I would size for this system if I was using lithium ion? I look at my daily load. In this case, it says 30 kilowatt hours per day. We decided we only need a 6-hour backup, right? So it's a quarter of a day. So I would take 30 times 0.25. That'd be kilowatt hours per day. And that will give me times 0.25, 7.5. I need a 7.5 kilowatt hour battery. That's it. They sell lithium ion batteries based on kilowatt hours, not based on amp hours. All of the D rates, all of the depth of discharge are already factored into those batteries. So when they sell you a Tesla Powerwall or something like that, and it says it's a 13 kilowatt hour battery, well, it's 13 kilowatt hours of production. So I could just go out and buy one Tesla Powerwall, and I'm going to have more than enough power if it's a 13 kilowatt hour battery. So sizing a battery when you're dealing with lithium ion is easy. Doing the old lead acid stuff, not so easy. This is one of the reasons why we're just in the process of finalizing the updated exam. So with the new exam that's replacing this one, we're getting rid of these lead acid battery sizing. But you will see a lead acid battery question on the test. Anybody have a question about that before I clear this off? I know I'm all over the place here. I want to give you guys the opportunity to say I am just totally confused. Usually when I go through these, it's pretty straightforward as I'm explaining them. The real trick is when you're taking the test and you're faced with doing it on your own. And then you're like, geez, I don't even know where to start. So that's why I always try and say that the thing that helps me is to say, okay, I'm starting with my daily load. Now, how do I get from daily load to the place I need to be, which is amp hours for batteries and it's kilowatts for solar array? Okay, so I just given you 3 of these questions, right? Sizing an array, doing voltage drop, and doing battery bank sizing. Now, to me, the most difficult of the math questions has to do with string sizing. And string sizing is also getting kind of antiquated because we're mostly using power optimizers and microinverters. But so the question is going to be, you've got all of these situations. It's going to give you a lot of things. It's going to say the solar panel that you're using is this with a VOC of this and a VMP of that and an ISC of this and an IMP of that. And here's the coldest temperature ever experienced there. Here's the hottest temperature ever experienced there. What is the maximum? Oh, and this is the size of the inverter. And what is the maximum number of panels that you can hook up in a string? So that's kind of how it's going to be presented. It may even tell you the barometric pressure is this and your wife's middle name is that. It's going to give you other information you don't need to know, but it will give you all the information that you do need to know. And so how would you size a string? Well, let's just back up a little bit and say, what are we talking about? When we hook up solar panels in a string, and we've got these panels, and they're hooked together, positive to negative, positive to negative, positive to negative. What happens when you do a series connection? Voltage increases, amps remain the same, right? So if my VOC, in this case, because VOC is the worst case voltage, if let's say the VOC of this is 31 volts of each panel, and I've just hooked up 4 of them in a string, what is the string output? Well, it's going to be 31 plus 31 plus 31 plus 31, right? Volts accumulate when you hook them up in a string. So that's going to be 124. Is that right? 124 volts. Okay, so that's how it is. Well, what happens if these guys are now being connected to an inverter, a string inverter? And the maximum voltage this string inverter can handle is, let's say, 550 volts. Well, how many panels could I hook up together before I exceed the maximum capacity of the inverter? Well, pretty straightforward. I take 550 and I divide it by 31, right? So if I take 550 divided by 31, it gives me 17.74. Well, I couldn't do 18 because that exceeds it. So I would round down and it would say 17 panels max. Okay, but there's a problem with that because temperature affects the amount of voltage that that panel will produce. So this is what it would be if temperature didn't affect it, but temperature does affect it. The colder it gets, the more the voltage that panel will produce. How much more? Well, that's the temperature coefficient, the TC at VOC. Well, let's look at the solar panel, and the temperature coefficient says, in this case, it'll be 0.4% per degree Celsius. So it's saying, okay, for every degree Celsius that it exceeds or it's below standard test conditions, because this number is given to you at standard test conditions, it's going to increase 0.4%. All right. So what does that mean in the real world? Well, we know all of these numbers have been based on 25 degrees Celsius. So I need to know what's the coldest temperature that site has ever experienced. So if that site, if I look up on Google Earth or whatever, and let's say that it's experienced minus 20 degrees Celsius, and we know that this number comes from 25 degrees Celsius. So the delta between minus 20 and positive 25 is going to be 45 degrees Celsius. So there's a 45-degree difference between the coldest temperature that might ever be experienced on that site, at least historically, and what temperature this number was measured at. So it's a delta of 45%. How much does the temperature, how much voltage increase per degree Celsius? Well, 0.4. So I'd multiply 45 degrees Celsius times 0.4% per degree Celsius. The degrees Celsius cancel out, and I get 45 times 0.4. 45 times 0.4 gives me 18%. So what did that just tell me? It just told me that on the coldest day that this location ever experienced, that panel will produce 18% more voltage than it will under standard test conditions. More voltage than what? More voltage than what was given to you at VOC. So I would take 31 volts times 118% or 1.18, and now I get 31 times 1.18. So that's going to be 36.58. So what did all that jumping around mean? It just means that if we experience again the coldest temperature that has ever been experienced at that site, that panel's not going to produce 31 volts. It could produce as much as 36.58 volts. So now I take my 550, which is the maximum of the inverter. I divide it by 36.58 volts, and that's going to give me my true number. So 550 divided by 36.58 gives me 15.03. 15.03, I'm going to round down, so 15 max. So that's a lot of jumping through hoops to figure this out. Now, my little trick that you can keep in mind is this first part was pretty straightforward. Take the maximum voltage, which is the VOC, divide it into the inverter's maximum voltage, and it gives you a number, 17. On a colder day, it's going to be more than that. So guess what? It's probably going to be less panels. So if I were guessing, I would guess either 16 or 15. You know? So if the answers that are given to me are 21, 19, 17, 15, and I do just the first part and I come up with 17 and I say, well, it's going to be less than that, I'm just going to guess 15. I don't even have to go through all of this stuff, but I want you to, I want you to understand it. But I'm just saying that if you're in the test and you're like going, oh, geez, I don't know, I'm so confused, this thing is really crazy, just know that the colder it gets, the more voltage it's going to generate. So I can only hook up fewer panels. Otherwise, I'm going to exceed that voltage. Okay. Does that make sense?
I had a question on that. That's the concept I don't get is when you go from 18%, how do you get it to 100%? They go 31 times 1.18.
Oh, yeah. Well, what we're saying that the panel is going to produce more voltage. How much more? It's going to produce 18% more. So that means it's going to produce 118% of what it would produce at standard test conditions.
Okay. Yeah, that was my question.
Yeah. It's not going to produce just 18%. It's going to produce what it already produced plus 18%. So now, contrarily, if we're gonna do the minimum in a string, so the concept of what's the minimum, we just figured out what the maximum is. We can't have more than 15. But what about the minimum? Well, the same thing applies really, except now we're saying, okay, what voltage does this inverter need to turn on? And normally these ranges, I'll tell you, a typical string inverter in today's market is going to go from about 100 volts to turn on and 600 volts maximum. Why 600 volts maximum? Well, if it's a residential system, we're not allowed to exceed 600 volts. So why build capacity into it that otherwise, you'll never use? So it's normally going to be somewhere around 100 volts to turn on, 600 volts is too much. Well, what do? when we're hooking up, I need at least 100 volts. Otherwise, there's just no point. So instead of VOC, now I'm going to look at VMP because I want to err on the downside. So let's say the VMP of this panel was 27 volts. How many do I have to hook together to get at least 100 volts to start this up? Well, I could do it if temperature wasn't a factor. Again, I would do the division. I would divide 100 by 27. It's going to give me 3 point something, but I need 4, because I got to exceed 100 volts. So I'll need at least 4 if temperature wasn't a factor. But we know that temperature is a factor. But now we're not worried about the coldest day ever. We're worried about the hottest day ever. Because the hotter it gets, the less voltage that panel is going to produce. So now I have to find out, okay, well, we knew it was minus 20. What's the hottest? Well, maybe it's 40 degrees Celsius. What's the difference between 40 and 25? Well, that's going to give me 15 degrees Celsius. But, and here's sort of the rub, if you've ever worked on a roof, you know that it's hotter up on the roof than the ambient air temperature. So the heating and air conditioners have given us a little guide. They've said if it's a ground-mounted system, add 25 degrees Celsius. If it's a ballasted rooftop system, so basically if the panels are sitting more than 6 inches off the deck of the roof, add 30 degrees. And if it's a flush to roof mounted system where the panels are less than 6 inches, add 35 degrees. So if this is a flush to roof system, I'm going to take my 15, I'm going to add 35. And so now I've got a delta of 50 degrees. Well, the temperature coefficient, now it's not going to be the TOC at VOC, it's going to be the temperature coefficient at VMP. But they usually don't give that to you. They usually give you the temperature coefficient at the maximum power point, which is the same thing. I don't know why they get into that, but they might say at the P max. And it's usually going to be something a little less. So let's say it's 0.36% per degree Celsius. All right, so we've taken 27. Well, we know that for every degree, it's going to be 0.3%, 36%. So in this case, it's going to be a delta of 50 times 0.36% per degree Celsius. The degree Celsius cancels out, and now it's going to be 50 times 0.36 gives me 18% again. What do you know? So it's going to be 18% less efficient, less voltage on the hottest day ever experienced. So in this case, now I take 27 volts times 100% minus 18%, so 0.82, 82%, and 27 times 0.82 gives me 22.14. So on the hottest day ever, it's only going to produce 22.14 volts. On the coldest day ever, it's going to be producing 36.58. That's quite a range, right? So what do? Is I take 100, I divide it by 22.14, and now I'm going to need 5 panels, right? I don't know exactly what it is. It's 100 divided by 22.14 gives me 4.5167. Well, you need more. You've got to round up. So it's going to be 5. So 5 panels minimum, 15 panels maximum. So that would be the answer. But if I did just this first step where I said, let's divide 100 by 27, which is the VMP, that gave me 4 panels. And then I'd say I probably need more than that because they produce less when it gets hot. So 5 seems like a good guess, you know? So that's a quick way,
Guessing
but
strategy.
you can go through all of these. Great. Do it. I hope, get the right answer, get exactly the right answer. But when if you're stressing about it, because as I'm explaining it, I mean, I've done this 100 times, so it's easy. It's
Mhm.
easy for me, but this is all new to you. So you've got to remember it's not hard, but there are a lot of steps in there that you've got to remember. So I'm just trying to give you a little bit of and literally in your mind, this is what you should be doing. All right, 27 volts. I need 100. That's going to be about 4, but it doesn't work quite as well. It's probably going to be about 5. That's kind of what I would do if I'm looking at a problem like that, just trying to figure out strings. So 5 minimum, 15 maximum. Well, what would be the situation? Let's say that my whole solar array is, let's say it's 32 panels. How many strings do I need? Well, all the strings have to be identical. So ideally, I would love to do 2 strings of 16 because the higher the voltage, the less the effective voltage drop, the smaller the wire, less components. All of it's good when you can push the voltage up as high as possible. But I'm being told I can only go 15 max, and 2 strings of 16 exceeds that parameter. So now I've got to go with 3 strings. 3 strings of what? Well, they've all got to be the same. So in this case, it would be 3 strings of 12? No. 3 strings of 11? Can I make this 33 panels? Maybe I can. Maybe I oversize my array just so that I divide evenly into that. So that's what I might do is add an extra panel just so my strings all work out. Because
AJ,
otherwise 32 I might have to go to what?
8 times 4.
8 times 4, so I'd have 4 strings of 8. Well, now we're starting to get down near the minimum, and
Yeah.
you're going to get more
4.
components, more voltage drop, bigger wire, all of that. It's going to add a lot of cost to the system. So I'd be tempted to go to 3 strings of 11. Or I might even be happier to change out my inverter and go with 2 strings of 16 if I can find an inverter that goes to 600 volts, not 550, which is what we made all those calculations at. If we go to 600, I'll bet you we can go with 2 strings of 16.
I have a
So
question.
yeah, go for it.
How come the strings do all have to be exactly the same?
It's because you're going to hook them together in parallel, either in the
Mhm.
inverter or in a combiner box. And if you've got different voltages coming in, hooking into each other, then you're changing the voltage. You're basically dropping it down to whatever the lowest common denominator is. So they just need all of the strings to be balanced. So
Gotcha.
now this is one reason why microinverters. Oops, I don't need to do that. Uh, Microinverters and power optimizers become a great solution, right? Because I don't have to go through all that nonsense. I'm, I'm not doing strings. How do you do a string calculation for a microinverter system? One panel, one microinverter. I got 32 panels. I got 32 microinverters. Boom, it's done. That's it. That's all my calculations. How do I do calculations for power optimizers? Well, I look in the manual that they just sent me, and it says the maximum number of optimizers you can hook together is 28. The minimum is 11. And it doesn't really matter what your system size is because these things manage themselves. So in that case, okay, if the maximum's 28, the minimum's 11, I'm going to do 2 strings of 16. That's just kind of, but I don't have to in those cases because I could do 1 string of 28 and 1 string of 4, and it would work because the voltages coming in are all still going to be, it's a fixed voltage system. So the only reason you have limitations on those strings is the amperage of your system. So anyway, so that's the microinverters. There are no strings, right? if I'm hooking one microinverter to one panel, what's the most I can put into a microinverter system? Well, let me share the whiteboard again. So what's the situation with a microinverter? Let's say I've got a bunch of solar panels here. And I've got a 350 volt or 350 watt panel. And my microinverter, I'm using IQ8 Plus and IQ8 Plus, which is Enphase's most popular residential. Well, it will output at 290 watts, right? That's its output. So if it's 290 watts, I can hook it into a 350 watt panel, no problem, right? Because of clipping. We've hopefully you've studied clipping. Well, what would be the inverter load ratio under that scenario? 350 divided by 290 gives me an inverter load ratio of 1.2, basically. Well, in today's market, an inverter load ratio of, say, 1.3 is about the most economical. And the reason is because panels are cheaper than inverters. And if we have an IV curve or a production curve, let's say this is your daily production curve on a sunny day, and this is your panel, this is your inverter. So if this is 290 and this panel is a 290 watt panel, well, that's the way it would work. So at solar noon, we're both breaking even. Let's say it's an STC day. But if I've got say a 370 watt panel, the production curve is going to look more like this. Well, I'm going to clip all of that because my inverter can't handle more than 290. It's just not going to produce it. Well, that looks like it would be bad, except we're getting all this extra production here on the shoulders, which may exceed what we're clipping off the top, even on a perfect day, even on an STC day. But most of your days aren't going to be STC. They're not going to be perfect sunny days with a temperature of 25 degrees and a radiance of 1,000 watts. Most of the days, it's going to be a jagged line that's going to be somewhat under the 290. So the bigger the panel, you're going to get closer to that 290. Your little panel might only be like this in comparison. So you just do better. You do economically better if you're getting about a 1.3 ratio, inverter load ratio. So that's clipping, all right? So I'm giving you sort of two concepts here. But if this is going out at 290 watts, remember it's coming out as AC electricity, right? So we're doing an inverter here, a microinverter here. It's connecting to your panel. And these guys are not connected in a string. They're connected in what's called a branch circuit. Why? It's because it's a parallel connection. It's not a string connection. Because the amount of power coming out of here now is converted to AC, and it's going to be 240 volts. AC. Why is it 240 volts? Because that's what the grid is. That's what you're connecting to. So the panels are coming out. So each time I add another panel with another microinverter into this string, I just said string, it's not a string, it's a branch circuit. What happens? Well, 290 watts divided by 240 volts gives me 290 divided by 240 gives me 1.2 amps. So every time I add one, I'm adding 1.2 amps, then 1.2 amps, and so on and so forth. So if there are only 4 panels, it's going to be 48 or 4.8 amps as I've hooked those together in parallel. So now my question is, what is the capacity of the wire that's hooking these things together? Well, the proprietary wire that comes with these inverters is 12 gauge, number 12 AWG. And if you look it up, 12 gauge is rated at 20 amps. But the NEC says we have to derate that by 1.25. We've got to have a little bit of extra capacity. So all that you can put on that wire is 16 amps. So what they do is they'd say, all right, everyone that I add is adding 1.2 amps to the mix. So how many 1.2 amps can I put into 16? And we get 16 divided by 1.2 gives me 13.3. So I could hook up 13. Well, if you look at the end phase specs, it says no more than 13 panels can be hooked up in a branch circuit. And this is exactly why. Because if you hook up more than that, you're going to exceed the ampacity of the wire that they sold you to hook these things together. So every branch circuit is limited to 13 panels based on the size of that microinverter. If it was a bigger microinverter, then you could hook up less panels until they put in a bigger wire. And they're only going to sell you, I mean, they're cheap. So they give you a 12 gauge wire. When they upgrade it to 10 gauge, we can go with a larger number of microinverters. But the proprietary wire that they sell at the moment is 12 gauge. So does that make sense to everybody? Why string calculations? I think I just blew your mind, but this is why. This is like learning French, right? So we're going to do 4 hours of review. But that one, to my way of thinking, is the hardest question, the hardest math question when you get into the string calculations. So that's why I give you that cheat of just taking whatever the biggest voltage is and divide it into whatever the biggest voltage your inverter can handle, and you're off to the races. You're close. You're going to limit it to 2 answers. Now you got a 50-50 shot. You're allowed to miss 18 questions and still pass the test. So what the heck, let's, so.
D's for degrees.
Yeah, there you go. When I was in graduate school, yeah, you had to have a B to get your degree. So everybody's like, I got an A, so now I can get a C. It's like, that was all anyone worried about, so get an A in the easy class because the C is coming. So, but not me. I was an overachiever. So, all right. I always say the only thing I ever learned in the MBA program is never to be impressed by anybody who has an MBA. So that's because they didn't teach me nothing. So it's sad. All right. Well, we've used up our hour. So any questions? This is well, feel free to give me a call or send me an email if you've got confusion about how to get here or the process that we're going to be dealing with over the weekend. I'm assuming all 5 of you are going to be here at the weekend. I did get confirmation. Yeah, I got a confirmation. Well, given air travel and everything else, but then also I know I got at least one other. So I think we're going to have 7 people, but we'll find out. All right. Okay, so I'll see you guys later and have fun studying. All right. Take care.
Thank you.
Bye-bye.